Sorry, guys, I was connected to our college Wi-Fi, but for some reason I cannot get this Zoom open from our college Wi-Fi. So type your attendance once again in the chat box. So I think we can discuss this IV characteristics later on. Today I'm thinking of covering this depletion width. Okay, so unfortunately, I forgot to carry my stylus pen, so I cannot use the stylus pen for writing on the screen. So let me see if I can use this mouse. I have one extra mouse, the department. Let's see if I can use this. Draw this up. The mouse. I left my pen for writing on the screen at home. So let's see if I can work with this mouse. Oh, this is so very uncomfortable. I don't know. I think I would prefer my touchpad. Okay, so let me start from here. As I cannot annotate. Can I write something using this? Yeah, now I can. But the problem is, will it remain on the screen? Yeah, it remains on the screen. If I use this annotate. How do I delete it? What is this? For some reason, this is again a very bad choice. This is not good. I'll just need to use a spot. And will it remain? And clear. Undo. Yeah, now I can do. Okay. So this is the depletion region that we talk about in the earlier lecture. And we have said that in the end side of the junction, as you can see, this is the junction. Let me write the junction. This is the junction point. Okay. So on the end side of the junction, the pentavalent atom, after donating the free electrons, extra electron, they become positive ions and they form the space charge region. And the charge density, the charge density in the region will be Nd. Nd is the number of pentavalent atoms per unit volume. Okay, here Nd is the number of pentavalent atoms per unit volume. So Nd, all those pentavalent atoms within this space charge region, they become a positive ions. And if you multiply with the electronic charge value 1.9 for minus 19 coulomb, then you can see the charge density within this region. The charge density within this region is E into Nd. And similarly, on the p side, of those trivalent atoms, after accepting the free electrons from the pentavalent atom, they become as negative ions. So there is a region of space near a junction, there will be a negative ions. And that region of space is called the depletion region again. And on the p side, since they are negative ions, so you can write the charge accompanied with each negative ions as minus of E, and Na is the density of this trivalent atom. Na is the acceptor atom density, means density of the trivalent atom in the p region. So if you multiply with the density, then you will find the density, the charge density within this region, the charge density within this region. Okay, so x0 is junction and x2 is the amount of distance up to which the depletion region is extended in the end side of the junction, and minus of x1. See, as you see, between x equal to 0 and between x equal to minus of x1, here you have a depletion region on the p side. So minus of x1 is the distance up to which the depletion region in the p side is extended. Okay, so the depletion region in the p side is between minus of x1 to x0. The depletion region in the n side is between x equal to 0 to x2. So if you want to calculate the depletion width here, as you see here, oh, I forgot to use the white screen. Oh man. So can you see this? Hello? Yeah,
Yes,
are you
sir.
following my lecture? Yeah. Okay. So I hope you understand what I'm saying here. So on the n side, you have this. This is the charge density, electronic charge into density of the donor atoms. On the p side, those acceptor atoms becomes negative ion. So the number density of negative charge is Na. You multiply with the electronic charge minus of E into Na will give you the charge density on the p region of the junction. And your depletion width extend from minus of x1 to plus of x2. So the depletion width here is between minus x1 to plus of x2. So if you measure a distance of between x equal to 0 to x2, the magnitude is x2. And if you measure a distance between x equal to 0 to minus of x1, the magnitude of this distance is magnitude of x1. So this will give you the addition of this width and this width on the p side. This will give you the whole depletion width across the p-n junction. And also, if you look at the potential problem here, on the n side there is a positive charge, positive ion. So positive charge is considered in a positive potential, and negative charge on the p side is considered having a negative potential. So the potential diagram can also be written like this. So at x equal to minus of x1, the potential is minus of v1, that is the potential is on the negative side. And at x equal to x2, the potential is on the positive side, that is above x exists. So on the n side, because of this positive ions, the potential is taken as positive plus v2. Here on the p side, it is minus of v1. So the whole potential barrier. So what is the potential barrier? Potential barrier across the p-n junction is, if you draw a straight line here, so if you draw another straight line here, this potential difference, the distance between these two lines, that is the potential difference here between x2 and x minus of x1 point, this is your potential barrier. So the potential barrier that we talked about earlier can be represented like this. And at x equal to 0 at the junction, the potential is taken as 0 here. The potential is taken as 0 here at x equal to 0. And at x equal to x2, the potential can be approximated as certain plus value, let us call it v2. And at x equal to minus of x1, because of the negative ions, the potential can be taken as certain negative potential value, that is minus of v1. Okay, so the potential barrier will be the summation of the magnitude of v1 and the magnitude of v2. I hope you understand the depletion region aspect here, the potential problem here that we are talking about. Now, let me clear all these annotations. Yeah, then only I can move to the next page. All right, so that is the problem we are going to tackle here. Now, as I just said, the depletion region on both sides consists of fixed charges, right? So in order to reduce the electrostatic property, the equation that describes certain fixed charge distribution in a region of space is Poisson's equation. So using Poisson's equation, you can describe the potential problem. Poisson's equation gives you del square V, V is the potential, equal to minus of rho, the charge density, upon epsilon, permittivity of the medium. So permittivity of your semiconducting medium, rho is the charge density, right? So in one dimensional problem, the Poisson's equation further reduces to d square x, d square V upon dx square. Instead of writing d square upon dx square plus d square upon dy square plus d square upon dz square for the 3 dimensions, in one dimension you can simplify it to this. So if you consider the p side of the depletion region, the p side of the depletion region is extending from minus of x1, there should be 1 here, minus of x1 to 0, as you can see here, minus of x1 to 0. So in this region, rho, the charge density will be minus of E into Na here, like I just explained before. So minus of E into Na. So you can put all this charge density value here in this Poisson's equation for one dimension. So this is what you will get in the Poisson's equation for one dimension. Now, moving on, if you integrate along the x-axis, so a single integration will give you this d square v upon dx square becomes dv upon dx. And once you integrate this quantity with respect to x, E and A into x upon epsilon. Okay, so there is a x into epsilon and plus certain integration constant. And at x equal to minus of x1, dv upon dx is 0. See, if you look at this simplified potential problem here, at x equal to minus of x1, the voltage is now constant. And between x equal to minus of x1 to x equal to x2, the potential is increasing with respect to x. So if you change the value of x, that is from left side to right side, if you go from left side to right side, if you move, your potential is climbing up from minus of v1 to plus of v2 here, between minus of x1 and x2. But at x equal to minus of x1 and at x equal to minus plus of x2, the potential is now having a constant value v2 for the n region, v1 for the p region. Okay, so considering that since the potential is now constant at x equal to minus of x1, dv upon dx is 0. So you put the value of x equal to minus of x1 here in this equation, here in the above equation, here you can put this. So you can calculate the value of C1. C1 you can obtain it as this. And then just by putting the C1 value here in this expression, you will get dv upon dx is equal to this. Then again, you can make it simplified a little bit, take the common factor and can write it like this, and then integrate with respect to x again. So if this quantity is, if you are integrating this quantity again, so unfortunately, with respect to x, here you see that x means integration of with respect, dv upon dx integration means v only, and you integrate x with respect to x, this will be x squared upon 2. Integrate x1, which is constant with respect to x, x1 into x. So x1 into x here, x squared upon 2, x1 into x, and certain integration constant C2. So now again at x equal to 0, if you remember in the problem here, I said that the potential problem is that such that at x equal to 0, the potential value is 0. X equal to 2, potential value is v2. X equal to minus 1, x1, the potential value is minus of v1. So at x equal to 0, the potential is 0. So x equal to 0, v value is 0. So you put the value of this. After substituting this, you will find that your C2, the second integration constant, is 0. And you can write your v as this, and then you can write at x equal to minus of x1, your v value is constant, which is v1. So v1 will be equal to E and A. At x equal to minus of x1 means minus of x1 square means plus of x1 square plus x1 into minus of x1 means minus of x1 square, minus of x1 square. Okay, then you can write v1 is equal to minus of this. You simplify it, this is what you will get. You will get the value of v1, and the magnitude of v1 you can write it as this. Just taking the magnitude means this is plus of this. Okay, so I don't have my stylus pen, so I hope you can follow the step. So if you remember the beginning, the description of the potential problem, then I think it should not be a problem to follow this lecture. This is just certain mathematical steps only. a differential equation solution of differential equation, because we have reduced our p-n junction problem into one-dimensional Poisson's equation. So we are just solving that differential equation, that is a Poisson's equation, one-dimensional Poisson's equation. Okay. Now coming to the inside of the region, we know that x equal to 0 at x equal to 0. The inside of the region is between x equal to 0 to x equal to 2 x2, and the charge density, like I described before, it is donor atom density into charge, unit of charge, that is 1.19 per minus 19 coulomb here, into number of donor atoms per unit volume, nd. So you put the value of your charge density here in this Poisson's equation. So this is this being a, here you see that this being a positive ions here, you put a plus sign here, and here you have a negative ions formation in the n side, p side of the junction. So therefore we have put minus e there, right? So following that discussion, here you can see that you can just put your your charge density in the depletion region on the n side as E electronic charge, magnitude of electronic charge multiplied by donor atom density. Now this again is simply a one-dimensional differential equation. You can solve it by taking integration again. So integrate it once, then you will get dv upon dx, and there is an integration constant, and once you integrate certain constant value on the right hand side, then there will be an x term here. So if you follow the integration formula, I think you will easily follow this step. And we know that at x equal to x2, like I said before, for the case of p region, dv upon dx is 0, because here in this figure here is, you can see that at x equal to x2, your v value is constant as v2, your potential value is constant as v2. Okay, so therefore dv upon dx is 0 at x equal to x2. Then by putting all these values, x equal to x2 here, you can calculate your c1 value, and then by putting c1 value in this equation, this is what you get. And then you do the integration once again in this equation. Integrating once again means integration of dv will be v, and integration of minus of x will be x square of minus of x square upon 2. This will be x2 is constant, so x2 into x, so plus certain integration constant c2 here. And again in the potential problem, we have assumed that at the junction, that is at x equal to 0, your potential is 0, like this. Okay, so at x equal to 0, your potential value is 0, because it is changing from minus of v1 to plus of v2. Therefore, considering for the fact that x equal to 0, your v value is 0, then you can calculate that your c2 value is 0, and you can obtain your v value. And we know that at x equal to x2, your v value is equal to v2. X equal to x2, your v value is equal to v2. So you just put the value of v2 here, and put the value of x2 here, x2 square. X2 into x means x2 square here. Then simplify it. This is your v2. So this is the magnitude of your v2 here. Okay. Now the potential barrier, as I said, this will be a summation of magnitude of v1 and magnitude of v2. Then you just add these two. This is what you get as a potential barrier. And here, nd is the number density of the donor atoms. Now, what is the volume of, if you want to know the, say, here E into nd is, as I said, this is the charge density. If you want to know how much charge is available here, you can do it by multiplying the density with respect to volume of the region here. What is the volume of this region? The volume of this region will be, what is the length now? Length is x2, that is 0 to x2. That means the length is x2. And if you want to find out the volume, you have to multiply the length with the cross-sectional area here. Okay. If you want to find out, this is the depletion region. If you want to find out the volume, then this is the cross-sectional area. A is the cross-sectional area, and this length is your x2 in the depletion region of n side. This length is x2. So if you multiply the number density of positive ions, that is Nd, number density, multiply with volume. Volume is x2 into A. So if you multiply this, you will get the amount of positive charge on the n side. And similarly, you can multiply your Na, number density of acceptor atoms, Na with what is the length here, x1 into cross-sectional area, that is the volume. You will get the amount of negative charge. And we know that the amount of the total number of positive charge on the n side and total number of negative charge on the p side, they are equal. Why is that? Because the negative ions on the p sides are formed after donation of electrons from the n side. So electrons from the n side migrate, diffuse, and donate their free electrons to the p side, the acceptor atom on the p side, thereby forming negative ions on the p side and positive ions on the n side. Therefore, the number of positive charge on the n side and number of positive negative charge, the amount of negative charge on the p side will be equal. So therefore these two quantities are equal. Let me delete all this thing again. Now, yeah, so here you see that Na into x1 into A, that is the number density into volume of the depletion region on the p side, volume of the depletion region on the n side, that is x2 into A into Nd, they are equal. So x2 and x1, they are related as this. If you substitute the value of x2 here, substitute the value of x2 here from the equation 4 into equation 3, you can have an expression of Vb like this, expression of Vb. And here, if you simplify further, you can write your x1 value like this in terms of Vb. So just put the value of x2 as this and then simplify further, then you will get the value of x1. And similar to that, you can also substitute x1 as this. So you can write your x1 as this, right? Then substituting in equation 3, put the value of x1 as this is equation 3, then you will get an expression of x2 like this. Get an expression of x2 like this. So then after that, the depletion width is which is simply magnitude of x1 into plus magnitude of x2. You can add these two quantities. Then after adding the x1 and x2 magnitude, this is what you will get as your depletion width. So the depletion width, as you can see, the depletion width of a potential barrier is directly proportional to the barrier potential. It's also proportional to the acceptor and donor density. So depending on whether you are having a high concentration of donor atoms and acceptor atoms or not, your depletion width will change. Okay, depletion width will vary according to the donor atom density. Okay, the doping concentration, you should say, the doping concentration. Now, what is the important conclusion we can have from here? Increased doping density in the p region results in decrease of depletion width in the p side of the junction. Okay, see, if you increase the value of Na here, see there are two Nas in the denominator, increase the value of Na, doping concentration on the p side, then the depletion width will decrease. And similarly, if you increase the value of Nd, doping concentration on the n side of the junction, then your depletion width will also decrease. So you can change the depletion width by controlling the doping concentration. You can decrease the depletion width by controlling the depletion. You can decrease the depletion width by controlling the doping concentration. Okay. Now, if you connect certain external forward bias voltage, so forward bias voltage, as if you remember in the previous class, we said that this is opposite to the barrier potential. So if barrier potential is taken as plus VB here, forward biasing voltage will have to be minus of V here. So if you connect certain forward bias voltage, then you see that the depletion weight X is proportional to square root of VB minus V. So increasing V means you are decreasing your X value. So the depletion weight also will decrease with forward bias. So when you connect a forward biasing, the depletion weight will decrease. However, when you connect a reverse biasing, the reverse bias potential is added to the potential barrier. This I discussed yesterday. Please revise my note yesterday, or my lecture. So when you connect in a reverse biasing condition, the potential connected from the external battery source, they will have the same direction as the potential barrier. Therefore, VB plus V. So that means your depletion weight here, X, will be raised if you add reverse biasing voltage here. If you add reverse biasing voltage, depletion weight X will be raised. Okay, so this will result in an increase of depletion weight. So the depletion weight across the PN junction is not a certain constant. It is certain quantity which you can control by controlling the doping concentration and by connecting biasing voltage, whether it's a forward biasing or negative reverse biasing. Depending on that, the depletion weight also will vary. Okay, so that's all I should cover for the electronics lecture. Give me a 10 minutes break, and then after that we can start C++ again. So I will give you a link for C++ class after this. So we'll take another roll call, another round of roll call again in that C++ lecture. So go through the notes because I have already given you the notes. As I said, copy down everything on your notebook, personal notebook. And while you remember this classroom lecture, please copy down your notes on your own personal notebook, exercise book. Then I think you will understand what we discuss in this very, very short period of time. So I think I can stop now. And I think we can start our class at maybe 1:45. I just need a few minutes break. Okay, 1:45 we can start.